Hey y'all, this is not going to be super entertaining, but hopefully it will be educational. If you come across a word problem where you have a lot of movement that is described to you in vector format, right? Like you're given horizontal components and you're given maybe vertical components, or you are given directions like south, or you have a picture like this, 20 degrees, and this is 22 miles per hour, or this is 200 miles per hour south. Once you have this movement that you are given, a series of movements in these word problems, what you're going to be asked to do is then change all of those movements into vector notation. So, for example, if you were talking about 200 miles per hour south, that is showing zero amount of movement in the horizontal direction, but in terms, let's call it horizontal or the X. And then it is going to be in the Y direction, the vertical direction. For thinking about a compass in the Y direction, this is going to be negative 200. So for every phrase you're given, you're kind of going to be tasked with describing the horizontal movement of it, the vertical movement of it in vector notation. So go ahead, if you have not written all of this quite yet, pause the video and catch up. So that is one way that movements are going to be described to you with these north, south, east, west. Sometimes you are given instead this picture of the vector moving. You're given a degree measure of that movement, and then you're being asked to turn that into vector notation, which you have been taught to do. Let me scroll up here. You have been taught to do with these mnemonic devices, these trig functions, so, ka, and then toa, we're not going to be needing right this second. So let's say that the vector is moving at 22 miles per hour, and we're given the degree measure of 20. What we're going to do now is we are going to set up our trigonometry functions so that we have sine of the angle 20 is equal to this ratio that's set up within this right triangle here. So the angle or the length measure that we're determining right here is the opposite side if we're using sine, right? The opposite side if we're using sine. So we are going, and this is a y value. So maybe you want to use opposite, maybe you want to use y. I'm going to use y for the sake of putting it in vector notation later. We're going to put that y value over the number 22. The same thing is going to happen for cosine. Let me skip a little bit of space. If you're taking notes, skip a little bit of space. Cosine is going to be helping us determine the length of the adjacent side, the side that is right next door to angle 20. It is the x value, the x movement. In this case, it's a negative value, right? We're going left or we're going west in this case. The x value of this vector, we can make a note for ourselves right there that it is going to be negative so that we can go ahead and make sure that in vector notation we are taking into account the directionality, the horizontal and vertical movement. Okay, so we have now placed x over 22 because this ratio of these sides is going to be equal to cosine of 20. Now, when we're putting these into our calculator, in order to generate this value y, we're going to type in 22. Then we're going to hit our sine key. Then we are going to write in our angle value. You can close the parentheses or not, and then hit equal, and a value that is generated here will be equivalent to the length right here. Okay, I'm going to pause and do that on my calculator. Pause now if you haven't already and type that into your calculator. Okay, what you should have generated is 7.5. Again, let's just go to the tenths place here. We're going to do the same thing for cosine. We are going to type in 22 and then the cosine key. Then we are going to input the angle 20, close the parentheses, and hit the equal sign. Go ahead and do that now. After you've input that into your calculator, you get 20.7. 20.7. Okay, so we have now done what we set out to do in this first step. We have described this direction that we were given in vector notation by describing its horizontal movement and its vertical movement. Then we have taken this drawing and applied trigonometry knowledge that we have to it in order to generate this vector notation. Now we have these two separate vectors, but remember the resultant vector, I'm going back up, hopefully you have space to start writing this. The resultant vector, switch to black, is going to be the next step that we are figuring out. So in your notes, let's add up these two vectors to get the resultant vector. Basically, the only clue we need to give ourselves is that we add them up. So lining them up, we have 0 and negative 200 describing the horizontal and vertical movement in the first piece, and then we have negative 20.7 and was it 7.5? 7.5 being described in the next piece. In order to add these up, we're going to add these two numbers and add these two numbers to get the resultant vector. So what comes of that just needs to be put into your calculator. Do that at this time, pause and do that on your own calculator. We add 0 and negative 20.7. We have negative 20.7, and when we add negative 207.5, we have negative 192.5. This is the resultant vector. Again, this part right here is describing the horizontal movement overall, accounting for both moves, and this portion is describing the vertical movement overall. Basically, we have to the left sum and down sum. So if we're trying to visualize this, I'm going to scooch that up. If we're going to visualize this, because the horizontal movement is this direction and the vertical movement is down, our vector is going to be in this direction. Hopefully you can see how that's coded into the negative numbers in our understanding of the coordinate plane. Now again, this is describing movement. That's good. That's what we need in order to get the next components, but we're not quite done with what we need to do. So that was the second step. We were finding the resultant vector by adding up the two movements described in the word problem. The third thing that we are going to do with that piece of information is then get both the components that we need for a vector to be fully described, right? We need both the magnitude, the length of that hypotenuse, and we need the direction. Otherwise, a vector is just lost without having both of those things. So as we are finding those things, let's label this next part magnitude for ourselves, and realize that we have two of the very important pieces that we need when we are looking for magnitude right here. We have the two legs of a right triangle, and we're missing the hypotenuse. Oh, if you said Pythagorean theorem in your head, you're right. So we're going to go to good old Pythag and use his stuff to get our stuff, okay? So we are going to put in our two legs, a squared 20.7. Now we can just kind of do the absolute value of these because we're talking about the length of that leg. So a squared would be 20.7 squared. B squared, again, I'm dropping that negative sign because 1, if you multiply a negative times a negative, you'll get a positive. But 2, I'm really talking about the length of it because magnitude is a length and the negative length is talking about the direction. So I can kind of drop that if I need to. And that will generate c squared. Now, I'm going to tell you that you put the keys that you're going to type in on your calculator. You type in 20.7, then you type in the squared button, the plus sign, then you put in your next number, 192.5, then you put in your squared sign, and you get this big number, right? But if you're working on a Texas Instrument calculator, you're probably going to end up hitting second in order to get your radical sign, to take the square root of it. And then if you are looking to input this answer right here, once you have hit this sign, you can then hit, again, you can hit second, and rather than transferring every digit from this answer, you can hit the, at least on my calculator, it's the key if you hit negative. Above negative, it should say something like ants. And it'll take this and pop it in right there. And you will then get the square root of c squared, which will generate for you c. Again, c is the hypotenuse, and in this instance, c is going to be equal to the length or the magnitude of that vector, the total vector. We're going to move on to directionality now. Okay, the next thing that we're going to do, in finding, let me remind you what's up here. In finding a vector to generate our answer in this word problem from the resultant vector and all those movements that described, the end vector, we've determined its magnitude, which is that hypotenuse length. And now we're finding this direction. So I'm scrolling down, and in your notes, you are writing the step B for this next part is to determine its direction. The formula that you're going to need to do this is tan or inverse tan, tan inverse, I don't know how you say it, inverse tan, I think, is y over x. Now that goes back to the TOA, right? The TOA is going to be the opposite over the adjacent. What you also need, in addition to this formula, is you need this resultant vector. So the resultant vector of the two movements was negative 20.7 and negative 192.5. So now it's a matter of using your calculator. Again, let's just label these for clarity's sake, that the x and y here are going to be used and plugged into your calculator for this. So to get inverse tan on your calculator, you hit the second button and then you hit tangent. It generates for you the open parentheses. You input then the absolute value of the y value is fine, so just positive 192. And then, oh, you don't need a comma. It's not, what am I doing? You don't need a comma. You use the divide sign because this is division. Holy gosh. I'm trying, y'all. I'm trying. You hit the divide sign and then you type in 20.7. go ahead, pause, do that on your calculator right now. So second tan gives you inverse tan, and then you're putting in these numbers. Let's see what it equals. Hopefully you punched that into your calculator and you got 83.9 degrees. Okay, why is the direction going to be in degrees? Well, it's because the direction is best described as this angle measure. Now, using this resultant vector, what we have described here is that it is going to the left and going down. I'm going to go down on the paper just a little bit more. If we had been given a vector right here that was up and to the right, we'd have a positive number and a positive number, and we could just take that angle measure and say, yep, that's the direction. But if we had a vector that was noted by going left, negative, and up, then it would be shooting off into this quadrant. Okay, so this is the first scenario, the first quadrant. This is the second scenario, and it's shooting into the second quadrant. Now, what we would have to do here is once we got this measure, because we're measuring this triangle, we have to talk about it in relation to this starting point. So how much did this travel to get into the second quadrant? Because it always, in the way that we're describing it, is going to start in the first quadrant, and we're talking about how much it traveled. So you're going to take this degree measure and you're going to take 180 and subtract away whatever degree measure you got in order to figure out a vector that's living in the second quadrant. Now let's describe something that goes into the third quadrant. Something that goes into the third quadrant has gone left on the x-axis and it's gone down. So it has gone left this direction and down. That is something that has traveled into the third quadrant. And you are going to, with your calculator, you're just generating this little slice of pizza. That wasn't a helpful triangle. This little slice of pizza. So you have to take into account that you always originate here, just so we're all on the same talking point. You've gone a full 180 and some. Okay, so whatever you get on the calculator, if your vector's going negative like this, you take the number 180 and you add it to whatever amount was going on there. Okay, now in the fourth, so that's the third quadrant. In the third instance, you pass through the first, the second, and you're into the third. This is 180 plus. Again, this is different because this is 180 minus that amount. Let's go into the fourth quadrant, which you get to by going right, so positive in the horizontal, but down, negative in the vertical. So to get into the fourth quadrant, your vector will have this setup. In the fourth quadrant, what you're going to do is, again, think about your origination point here in the first quadrant, and you're traveling 180 and you're traveling 90 more, so 270 degrees then gets added to your angle amount. Or you could subtract from, yeah, just do that. We won't go into multiple options. 270 degrees gets added to whatever angle amount you have in the fourth quadrant. You can also think of it in relation to a full circle, 360, if that is easier. So hopefully those formulas are helpful to you in figuring that out. So now let's go back to the actual problem. We have 83.9 degrees, but that's not the truth unless it's living in the first quadrant. It's living in the third quadrant. Remember how we described it up here? Remember how we said it went left and down, so it's going into the third quadrant. So that means that whatever degree measure we have to take a full 180 and add it to that. So we're going to take the number 83.9. That's what we got for our triangle. And then we are going to add reality to it based on which direction it went. And we are going to say, hey, this is in the third quadrant. And in the third quadrant, which is shown here in this example, I need to add 180 degrees to make that the truth. So we are going to add, let me give myself a little bit more space, add 180 degrees, which will yield 263.9 degrees. We have our total magnitude. Super duper, where is it? We have a total magnitude. Where did it go? Did we ever write it out? This answer? I don't know. We have our total magnitude. Let me get it. I'm sorry, y'all. We didn't ever say what our total magnitude was, I don't think. I don't know, it's been a long video. I can't quite remember, and I made a few other mess-up versions of this video. I can't remember what I said. Once you've punched this into the calculator, you get 193.6. Again, we were working in miles per hour, so that will be our unit. At 263.9 degrees. So our total vector is represented there. We've got our magnitude, super. We got that using Pythagorean theorem. And then we got our direction, super. We got that using inverse tan and our quadrant math. So we have achieved vectorhood. And we win. That's the end. Reach out if you have questions.